All right, welcome. In this video, we're going to be talking more about quadratic equations. This time we're going to be talking about vertex form and completing the square. But first I need to remind you of a couple of special factoring cases. And the first is going to be a difference of two squares. And so I'm just going to remind you of something that you've already learned about, is that if you have a squared minus b squared, you can factor that up into a plus b times a minus b. And if you're not sure why that's true, then you should distribute a plus b times a minus b and see that that's going to come back with a squared minus b squared. Okay, and so when trying to factor the difference of two squares, something like this, I'm going to identify, hey, x squared and 4 are both squares, and it's a difference because it's minus. So I'm going to say that this is x squared minus 2 squared, and then I can factor that into x plus 2 and x minus 2. And maybe you don't always need to write it, that intermediate step as what are the two squares, but if you're having trouble seeing, then, that could possibly help, okay? I want you to try the next 7 on your own, so you can pause and then check the answers out, because they're about to show up. Okay, there you go. There they are. So, most of the first few were pretty standard, identify something like 64 is the square of 8, or 49a squared is the square of 7a. But then the last is a little something else. On the second to last one, 32 minus 8n squared, you needed to factor out the 8 first, and then it became a difference of two squares. And then that very last one, okay, probably where I expect you to be today is, to factor that up into x squared plus 1 and x squared minus 1. X to the 4, that's kind of beyond the scope of a quadratic unit, but I figured I'd show you where we're headed with this stuff. Okay, where we're going with this is we're going to look at this and say, oh, hey, x squared minus 1, that's also a difference of two squares. And we can keep going and say that's x plus 1 times x minus 1. Okay, but that's just a reminder of a difference of two squares. Next, I'm going to show you about the perfect square trinomial. Okay, now a perfect square trinomial is probably something you saw in Algebra 1. And with that one, if we have something, at least at this point, I'm just going to talk when the leading coefficient is 1. If we have x squared plus 2 times some number times x plus that same number that was doubled squared, that's something that we can factor into x plus a squared. And again, if you're not sure why this is the case, then you should go ahead and multiply x plus a times x plus a off to the side on a scrap of paper and see that that's going to be x squared, 2ax, and a squared. Okay, so perfect square trinomial, x squared plus 6x plus 9. In my classes, I told the students, just look at this, try to factor it the old way. What are two numbers that multiply to 9 and add to 6? Oh, 3 and 3. So this is x plus 3 times x plus 3. Maybe you recognize the pattern of x squared plus 2ax plus a squared, but I don't know. It sounds a little unlikely to me. And just remember that we always try to factor by finding two numbers that multiply to the last number while adding to the middle number. Okay, so this is x plus 3 squared. Okay, and then this one over here, I've got x squared minus 14x plus 49. So two numbers that multiply to 49 while adding to negative 14, that would be negative 7 and negative 7 again. So this is one I would factor with x minus 7 squared. Okay. Then over here, kind of the backwards line of questioning. What value of a would make this a perfect square? Well, okay, I can see that 25 is a square number. It's the square of 5. So I'm kind of like matching up over here. Okay. So if that's the case, then a would need to be, twice the number that's getting squared. Okay, probably poor choice of letters there, but I'm going to just say, all right, I would need a equals 10, right? Because then it would be x plus 5 times x plus 5, and I'd have, an x squared and a 25, but then when I did the outside and the inside, I'd have also 10 x's. Okay, now this last one, this is really where we're heading. What value of b would make this a perfect square? Okay, that's the question we're going to continually ask ourselves in this lesson. Okay, so what we're going to do is we're going to take this negative 12, take it off to the side. I'm going to divide it in half and then square it, right? Because I'm starting with 2a up here. I'll kind of point at that in pink. I'm starting with 2a. Okay, so negative 12 to get that a, I'm going to divide by 2. Okay, and then it's a squared is what I'm going to add out here. Okay, so if I take negative 12 and I divide it by 2, I'm going to get negative 6, and I square it, and that's 36. Okay, so that would need to be b equals 36 to make that a perfect square. Okay, and we'll talk more about that as we move forward. All right, now let's talk about vertex form of a quadratic equation. So we know that the standard form, I'm going to copy that in right now. The standard form of a quadratic equation is ax squared plus bx plus c. And I just want to remind you or point out that, I guess you wouldn't know that yet, so it's not a reminder, that this a is the same as that a and that a. It's the leading coefficient. It's the number that's telling us is the parabola opening up or down, and like how wide or narrow is the parabola. Okay, and so we can always go from standard form to vertex form by completing the square. And I'm going to show you what that means, completing the square. So I've got something like, I'm just choosing a color. I've got something like y equals x squared plus 6x plus 7. But x squared plus 6x plus 7 is not a perfect square. Okay, and I want to get a perfect square trinomial like right there, you know, like so that I can factor it up and make it look like that. Okay, so what I'm going to need to do is I'm going to figure out what would I need to add to x squared plus 6x to make it a perfect square, just like that last problem I did on the previous page. So what I'm going to do is I'm going to grab this positive 6 and kind of take it off to the side. And I'm going to say, all right, I'm going to take positive 6 and I'm going to divide it by 2, and then I'm going to square it. And that would be 3 times 3, which is 9. Okay, so that means that I need to add 9 to make this a perfect square. Okay, so I'm going to do that, plus 9. But in order to preserve the equality, in order to be fair to both sides of the equation, I need to add 9 to the other side as well. Okay, now I have not changed the equation. I've not changed the graph of the parabola is another way you can think of it. Okay, because I just added 9 to both sides. Okay, now after that, I'm going to block off this. Okay, the reason I added 9 was to make this a perfect square. The thing that I blocked off with square brackets, I should be able to factor that as a perfect square trinomial if I added the correct number in gray to both sides, right? So I'll have y plus 9 equals, when I factor this, I look, how can I factor x squared plus 6x plus 9? I'm pretty sure that was when we factored on the previous page. But that's going to be x plus 3 squared plus 7. Okay, but the vertex form is where we solve for y, and we have some number times x minus a number squared plus some other number. So I need to get rid of that 9 and say, all right, I'll subtract 9 from both sides. And that'll be x plus 3 squared. 7 minus 9 is negative 2. Okay, this is vertex form. Okay, the work that I did in yellow highlighter and gray or whatever, and I guess the next step of factoring, that's called completing the square. Okay, and I didn't change this quadratic equation, I just wrote it in a different form. But the form I wrote it in makes it very easy to see what the vertex is. I don't have to do negative b over 2a and then run that number through the formula. That's not going to be necessary. I can say that, okay, the vertex, or if it's x minus h, then the x-coordinate of the vertex is positive. So if it's x plus 3, the x-coordinate of the vertex is going to be negative 3. Really, it's whatever makes the thing inside the square equal to 0. And I'll have more to say about that when I talk about, the maximum and minimum possible values of these things. But for now, I'm just going to tell you this is the formula, this is the rule, we're just going to go with it. Okay, x equals negative 3, but k is the y-coordinate. I don't have to make it negative or anything. So it's going to be x equals negative 3 and y equals negative 2. And that's us writing a quadratic equation in vertex form. All right, because this is, kind of a trickier thing for most first-time Algebra 2 students. I'm going to do one more for you before I kind of like set you loose and have you try this on your own. Okay, so I've got x squared minus 8x plus 3. And then I might be even more detailed this time about how the factoring is going to always work. Okay, so I know that I'm going to need to kind of, x squared minus 8x plus 3, this is not a perfect square trinomial. 3 is not a perfect square, and it's definitely not the square of negative 8 divided by 2. Okay, so that's just not going to work. I'm going to set up to complete the square, so I'm going to add some space to add something to y, and then to hold on to x squared minus 8x, And one thing you can do is you can kind of like pre-block it off with square brackets to remind you that I'm going to be adding a number into that square bracket. And then I still have that plus 3 on the outside. You don't want to lose track of that. Okay. Then I'm going to determine what number do I need to add to both sides by taking -8, dividing it in half, and then squaring. Okay, well that would be -4 squared is positive 16. Okay, so I'm going to, pardon me, I've been using a different color for that, add 16 over here, and to be fair to both sides of the equation, I got to add 16 over there, right? Okay, now I can factor, but what I'm going to point out this time is that the number that I'm going to have, you know, with x, I'm going to just fill everything else in. That number that's going to go in there is this number right here, that -8 divided by 2. Okay, so that's going to be x minus 4 squared. And you can check that by using FOIL or just like kind of mentally thinking what's going to happen when I multiply x minus 4 times x minus 4. But that's how it's going to factor. It's always going to work like that, provided that you've completed the square correctly. Okay, so I'll just get rid of that arrow. And now I'm going to say, all right, I'm going to subtract 16 from both sides, and I get y equals x minus 4 squared minus 13. Okay, and that would mean that I've got a vertex where x is positive 4 and y is negative 13. Okay, now you try this next one on your own. Okay, you're going to work this on your own, and in a second I'm going to just flash up the answer, so you should pause now. All right, there it is. So I completed the square by dividing that -4 in half and then squaring it, so I added 4 to both sides. And then I factored and, you know, subtracted the 4 away, and I got my vertex at x equals 2 and y equals -5. Let's try 2 more. Okay, so these have a little extra layer of difficulty to them. They've got a leading coefficient that's not 1. And so I'm going to show you how to deal with that. Okay, so what I'm going to do is kind of set up kind of the same way. And that will be, you know, by adding room to add a number to both sides. Okay, but I'm going to factor out the 2. Now I'm only going to factor out the 2 from the things that have the x's on them. Because that 3, that's kind of, I don't know if you remember the last few, that number on the outside, I only just used that to subtract away something. It wasn't really contributing all that much. It was really only contributing to the y coordinate. We already know that the value of c in ax squared plus bx plus c, that affects the y-intercept, so that wouldn't be totally surprising. And we're just going to leave it be, right? So I'm going to factor out the 2 from the first two things, and I'll have x squared minus 4x. I'm going to leave room to add a number, and then I'll still have plus 3. Okay? Just like before, I'm going to take this -4, and I'm going to divide it in half and then square it to determine what number I need to add to complete the square. Okay, so -2 squared is positive 4. So I'm going to add my 4 right here. But I got to be careful at this point because, you know, whoops, lost part of my x. But if I just added 4 to the other side, that would not be fair. Okay, and I'm going to hopefully give you a second to try to think about why that wouldn't be fair. Okay, but it wouldn't be fair because if you think about it, what I've really added to the right side of the equation is a 2 times 4. Right, so I've added 8 to the right side, so I need to be fair and add 8 to the left side. Okay, and now I'm going to subtract, I'm going to factor first. Okay. And then this will be x plus that number right there, so x minus 2. You could also say it's half number in yellow highlighter. Okay, 2 times x minus 2 squared plus 3. And then I will solve for y by subtracting 8. So 2 times x minus 2 squared minus 5. And then my vertex, just like the last one, is at x equals 2 and y equals -5. It's just the difference is this one's going to be a little narrower. Okay, it's going to have different x-intercepts. Okay, and then over here, I think this is the type of thing that's very tricky for first-time Algebra 2 students, so I'm going to walk through this one with you as well. I'm not going to just be like, hey, you do it, and flash up the answer. So I'm going to leave room, factor out the -3 from both the x squared and the -3x squared and the positive 6x. So I'm factoring out a -3, and I'm left with an x squared minus 2x. right? Because negative 3 times negative 2x would be positive 6x. Okay, and then plus 1 on the outside. Okay, now I'm going to determine what number I need to add to complete the square on the inside of the brackets. And so I take that negative 2, divide it by 2, and then square it. And that'll be negative 1 squared is positive 1. So I'm going to add 1 right here, but I need to be careful because I had a leading coefficient that wasn't 1, right? So I really added a negative 3 times 1. So I added negative 3 to the right side. I need to add negative 3 to the left side. And then I'll factor. Okay, this is going to be x minus 1 squared. Or you could just think about what are two numbers that multiply to positive 1 while adding to negative 2, if that is feeling better to you. And then I still have that plus 1 on the outside. Now I'm going to add 3 over here, and I'll get y equals negative 3 times x minus 1 squared plus 4. Okay, and that will have a vertex at the point where x is 1 and y is 4. So that's how we're going to complete the square when the leading coefficient is not 1. We can also use this complete the square technique to solve quadratic equations, okay? Specifically ones that aren't factorable. If it's factorable, you want to solve by factoring. I'm telling you, it's the way to go. It's the most convenient way, and it's the way that is most commonly used in classes beyond Algebra 2. Okay? It's good that we know that we can solve equations that are not factorable. We can solve any quadratic equation, is what we'll learn in this class. But for now, I'm going to show you how. I'm going to start with one that's factorable, so that the numbers work out nice. But then I'll do one that's not factorable, and we'll see that it's still workable. So over here, I'm going to do the exact same thing. I'm going to say, okay, x squared x. I need to add some number to it to make it a perfect square. And I need to figure out what number that's going to be. So I'm going to take this positive 6, and I'm going to divide it in half and square it. So 6 divided by 2 squared, that's equal to 9. Okay. So I'm going to add 9 to both sides. Oh, I already had this 7. That needs to stay there. Okay, so I'm going to add 9 to be fair to both sides to not change the equation. Okay, and then now this thing on the left side is factorable. What are two numbers that multiply to positive 9 and add to positive 6? That would be positive 3 and positive 3. So I've got x plus 3 squared, and that's going to equal 7 plus 9 is 16. Then I'm going to take the square root of both sides of this equation, and I'll have the square root of x plus 3 squared equals the square root of 16. Okay, now in the last lesson I talked to you about how the square root of x squared is the absolute value of x. So the square root of x plus 3 squared is going to be the absolute value of x plus 3. The square root of 16, that's 4. Okay, and if the square root of, if the absolute value of x plus 3 is 4, then x plus 3 could be 4, or it could be negative 4. Okay, so I've got x plus 3 equals 4, or maybe x plus 3 equals negative 4. And I can solve these. X equals 4 minus 3, which is 1, or x is negative 4 minus 3 more is negative 7. And if you'd subtracted 7 from both sides of this equation, you could use the zero product property and some factoring and gotten x equals 1 and x equals negative 7 a whole lot faster. Okay, but I was showing you how we can always solve with complete the square. And this is not factorable. You can't think of two numbers that multiply to 2 and add to 4 because they don't exist. So what we're going to do is, well, that might not be true. I might be about to find two numbers that multiply to 2 and add to 4, but they aren't integers is what I'm going to say. So I'm going to go over here and I'm going to say, all right, x squared plus 4x. I need to, make some room to add the same number to both sides, but I still have this plus 2, and that's equal to 0. Because I know that here is going to be my square. So in order to figure out what number I need to add to complete the square, I'm going to take that positive 4, I'm going to divide it in half, and I'm going to square it. So positive 4 divided by 2 is 2. I square that, I get positive 4. So I'm going to add 4 to both sides of this equation. Okay. And now I will factor. Okay, this is going to be x plus 2 times x plus 2, so x plus 2 squared plus 2 equals 0 plus 4, which is going to be 4. Now I'm going to subtract 2 from both sides to isolate the square. Then I'm going to take the square root of both sides, and I'm kind of running out of room here, so I wasn't writing as small as I did the last time. Okay, and I've got the square root of 2. Okay, the square root of 2, I don't know, it's bigger than 1, but past that I'm not totally sure. And we're just going to leave it as square root of 2, especially because we have not studied radicals in this class. I think it's okay for me to expect you to know that the square root of 16 is 4 or the square root of 49 is 7. But other than that, we're not going to do anything special with radicals until later in the course when we actually study them, and then I'll expect you to do all sorts of special things with them. Okay, but at this point, I've got absolute value of x plus 2 equals square root 2. And maybe, to save some room, I can go over here and I can say, okay, if the absolute value of a thing is root 2, then that thing is either root 2 or it's negative root 2. So I could use a plus minus. So I could say x plus 2 equals plus or minus the square root of 2. And I could solve for x, by subtracting 2 from both sides. And that is, I guess, a safe place to stop. But I'd prefer if you displayed it as 2 separate x values to really remind yourself that this equation has 2 solutions. So I would do that by saying x equals negative 2 plus the square root of 2, or maybe x equals negative 2 minus the square root of 2. And then I really clearly have 2 solutions to this equation. All right, now it's time for you to practice on your own. You're going to choose a few of these, and you're going to work them, while you've paused the video, and then you're going to check your answers against mine. I would say, you might not need to do all 6 of these, but, choose a few of them that you think that would be, useful for you. If you're really getting it, try the ones that have a leading coefficient of x squared or t squared that's not 1. Okay, so maybe the last couple. But if you're really unsure about this, maybe just try the first 3 and then check your work. Okay, so you're going to pause now because the answer is just going to pop up in a second. All right, there you go. That was a lot. That was probably more examples than I should have put on there. I worked all of them just now, and it was kind of a marathon. Okay, there was some different things happening in the top right. We had one where when we completed the square, we had to add a fraction. Okay, that'll happen occasionally, but probably not too much in this class. And then, kind of in the bottom row, the pink and purple ones that I did, you had to kind of rearrange them first. And then I realized I wasn't using color to, denote when I was completing the square, so I went back and highlighted in gray. What I would say is that, I followed the same process on these that I did on all the other ones, but if you have any questions about these specifically, come talk to me about them. I'd be happy to talk with you more about these. All right, now I'm going to skip forward to where we're talking about increasing and decreasing and maxima and minima and stuff. Okay, and I did skip over a page in your notes, if you're following along in the notes book, about factoring. I'm going to record that as a separate video, because that's not really something we need for Algebra 2, but it's something cool we can do with completing it with the square. Okay, for now, what I need to tell you about is the increasing, decreasing thing. So if we've got a function, and maybe, okay, this is not the graph of a parabola, right, but it's just some function. Okay, maybe we'll talk about one that looks kind of like this later on in the course. And we know that this point is at, let's say, x is 4 and y is 9. And then we'll say maybe this is x is 5 and y is 2. I don't know, maybe it's not drawn to a very good scale. Okay, but I think that'll be good. A function is increasing when its graph has positive slope. Okay, well, we only talk about slope of lines, but I think you could say that, if I looked really closely at this curve, at, say, this point that I colored in red, if you look really closely, you see that it looks kind of like a line, and it's definitely got positive slope there. Okay, so I'm going to say that this function is increasing this whole time, right? Because these are all positive slopes. Now, there up at the top, we're having a 0 slope, because it looks pretty flat. Okay? And now the specifics of this that's what calculus is, so I'm not going to be, too detailed here. But also another kind of equivalent definition of increasing is as we move left to right on the graph is going up, okay? So I'm going to say that this graph is increasing from when x is less than 4 and also when x is greater than 5. And then I could say decreasing is where a graph has a negative slope, okay, or as I move left to right, the graph is going down, okay, that's going to be where the function is decreasing. So in this example, this function is decreasing between x equals 4 and x equals 5, so like this. And you can write these in interval notation if you like. Maybe the example I've got below, I'll do it like that. Okay, I also want to talk about a maximum and a minimum. Okay, a maximum is a place where the function goes from increasing to decreasing. Okay, so we're going to call that a local maximum or a relative maximum. I forget what terminology we use. We probably are going to use both of them. And then this is a little local minimum, because if we were to just zoom in and look only at that, we'd see that it was, at a minimum, at least 4 points nearby it, right? We can see way off to the left there are places on the graph that are below y equals 2, but at least locally, this is the lowest thing around. Okay, and a minimum is where a function goes from decreasing to increasing. Okay? So let's work a quick example. All right, so we're going to start off by sketching the graph of a quadratic equation. It's already in vertex form for us. That's nice. Okay, I've figured we'd done enough completing the square in this video that we didn't need to do any more. Okay, so we know that the vertex of this thing is going to happen at x equals -3 and y equals -4. And because of that -1/2, we know it's going to open down, and it's going to be, kind of wide. But I'm not really too worried about how wide it is. It's really just the general shape that we need to answer these questions, right? Because now if I see the vertex and I've got the shape, I can tell where it's increasing and decreasing, at least for a parabola, because parabolas are relatively simple graphs. Okay, f is going to be increasing over here where it's got a positive slope, where as I move left to right, the graph is going up. Okay, so f is increasing when x is less than -3. Okay, we could also say that's from -infinity up to -3. Okay. F is going to be decreasing where it has a negative slope. Okay, or where as I move left to right on the graph, I'm going down. So that would be where x is greater than -3. And that would be from x equals 3 up to, approaching infinity. Okay. F has a relative maximum at a place where f goes from increasing to decreasing. So that's going to be right there at x -3. Okay, and I just want to point out that when they ask a question like where, the answer to that is going to be an x value, right? Okay, but if they ask what is the maximum value of f, well, f corresponds to the y-coordinate, right? So the maximum value is going to be the y-coordinate of the vertex. Okay, so that's going to be, the maximum value of f is -4. Okay, now if I look at this equation right here, that I'm going to, I guess, put pink around. Okay, and you think about the squared item, the -1/2 of x plus 3 squared. Okay, x plus 3 squared, no matter what x is, it's either going to be 0 or positive. Okay, because if I take 0 and I square it, I get 0. If I take anything else and I square it, that comes back positive. So the very most, because of the multiplication by -1/2, the very most that -1/2 times x plus 3 squared can be is 0. And that's where we see that vertex. That's the most it can be. Any other x value besides x equals -3, I'm taking -4 and I'm adding a negative number. So that's why it's going down from there. So that's why we have a maximum at a place where the thing inside the square, when the quadratic is written in vertex form, when that comes back to 0. Okay, so that would be why, it's x minus h, but positive k, giving us a vertex of h and k. Okay, I think that's all I've got to say about completing the square in vertex form for today. We did a bunch of good examples. We're almost 30 minutes in, so I think I'm just going to say thanks for watching, and I hope this helped.